Okay, as a gentle reminder, there's no food or drink in the classroom. So, because otherwise I would have my beef chow fan with me right now. And my coffee. I had to pour cold water into my otherwise wonderful coffee so that I can actually finish it before the class because it was a little bit too hot. But it wasn't very enjoyable once I diluted it. I need to investigate those caffeine patches. So those are, has anyone tried those? Not the nicotine ones, but the caffeine ones. No one has tried those? Okay. I'm trying to find out whether they're actually effective or not. All right, so this is your next homework assignment. You kind of knew this one was coming because I have been talking about it for a little bit. It's called the omega generator. So the omega generator is for generating permutations. Okay, combinations are much more difficult to generate. So we are only going to generate permutations. So the program, as an executable, is going to parse 3 parameters. The first parameter is a base 10 number, that is the number of trials. The second number is the number of choices for the first trial. And then the last number is basically just 0 versus non-zero. It indicates whether the trials in the experiment are with or without replacement. So in this case, non-zero is with replacement, and then 0 is without replacement between the trials. Okay, so that's how the executable is going to be. So it has to interpret those arguments. The choices are represented by lowercase English letters. So that means from A to Z, you can have up to 26 choices. If trials are without replacement, the number of choices of the first trial is greater than or equal to the number of trials per experiment. Can be. Okay? So let's see. I'm just trying to point out where we are talking about here. So if trials are without replacement, then we have to guarantee the number of choices in the first trial is greater than or equal to the number of trials. So that's going to be guaranteed. You don't have to check for that. The output should be organized in lines, where in each line, each line represents a possible experiment outcome as a permutation, and then each line contains the lowercase English letters without separators, no space, no commas whatsoever. And I have several examples. So this is one example. /a.out is just how you invoke an executable from the command line in Linux. In Windows, it's a different thing, and then in Mac OS X, I think it's also a.out. So in this case, we have 2, 3, 0. The last one is without replacement. The 2 means we have 2 trials, and then the 3 means the first trial has 3 choices, which are the first 3 English letters in the alphabet, A, B, and C. So the output of the program is A, B, A, C, B, A, B, C, C, A, C, B as the permutations of the possible outcomes of that experiment. Is that okay? Okay. Another example. So 3, 2, and 1. So we have 3 trials per experiment, 2 choices for the first trial, but this time it is with replacement. So that's why the output is AAA, AAB, all the way to BBB. Is that okay? Because it's just, it's basically the same thing as a base 2 number with 3 digits, and it goes from 0, 0, 0 to 1, 1, 1. Because each trial only has 2 choices, and it is with replacement. So are we doing okay so far with the sample outputs of the program? Is that okay? All right. Okay. So as you can see, we are only concerned about permutations, because otherwise AB and BA would be considered the same combination. AC and CA would be considered the same combination, and then BC and CB would be considered the same. So generating combinations is considerably harder because we basically have to filter out things compared to generating permutations. So We only have to generate permutations in this particular program. So, so the program has to be done in C or C++ because the prerequisite of this class, or the co-requisite, is 430, which has 400 as the prerequisite of that. So I'm assuming that everybody knows how to program in C and C++. It doesn't have to be object-oriented, okay? In fact, I would, for something like this, I would kind of steer away from, real object-oriented programming because it's not going to buy you much, okay? All right, so we're going to talk about, how do you get started with a program like this? Because C and C++ has no internal type called set. So how do you implement the concept of a set when you do not actually have it as a built-in type? So that's kind of a data structure thing, but I would even say that it's not a data structure thing, okay? All right, so there are a few things, and also how do we get to these arguments on the command line, okay? Some people know how to do it because they have taken CISP 3, maybe 310. I don't know whether I did it in 310 or not. But I talked about this technique in some of my classes. All right, so are there any questions about the homework itself? The description of the homework assignment? Okay, no questions about what the program needs to do? Are we doing okay so far? Maybe? Okay, yes? It only takes letters. So if I have like 4 choices, then it will be A, B, C, or D as the first trial. But the second trial kind of depends on whether it's with or without replacement. If it is without replacement and you take A for the first choice, then the second trial will only have B, C, and D left as possible choices. But they're not digits, they're not numbers, they are lowercase letters. Okay, all right. So there are a few things I need to demonstrate and let you guys know how to do it. And the best way to do it is just to show you the code, and you guys can then use this as a basis, okay? In other words, what I'm showing you right now is something you can just copy into your own program if you want to. But the intention of what I'm doing right now is not for you to copy, it's to illustrate the underlying concepts that you will need to understand. Is that okay? All right, so let's go ahead and get started here. So I'll just call this omega. And as I said, just plain C should be fine. So we'll go ahead and start with main. But this time, you will need argc, which is a count of arguments. And also, the cons part is optional, but I would put it there anyway. And argv, which is a pointer to a pointer of cons chars. Now, the other way to look at this is to say it is an array of strings. Okay, that's an easier way to look at it. All right. So this is not something that you normally do with your other classes, because with your other classes, you typically do not pass arguments to the command line itself. But this is actually what is being passed to every single C and C++ program, even though you have not used that feature until now. All right, so the first thing we want to do is to see if we have enough arguments. In other words, we want to see if argc is, now you can compare to exactly 4 or at least 4, okay? But I'm just going to say exactly 4 here. So there's an else, and then we just put it return 0 here. So we'll just say printf. I know printf is, yeah. I believe so, but that's a good, yep, it is. Thank you for checking. Okay, so I'm just going to do a printf here. And you can do a whole bunch of stuff that you can print. I can print the 4 strings, for instance. So $s, 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 $s. And no, just 3, because the first one is actually predictable. So only 3 are actually useful. So this is argv1, argv2, argv3, like so. And this one is going to print not exactly 3 arguments. Okay. And of course, we need to do a pound include of stdio.h. Now this program, your program is not supposed to echo back the three parameters. That is not what your program is supposed to do. I'm only doing this as an illustration of what the program will do. Okay, so this is just for illustration purposes. All right, so here's the program: gcc-g for debugging, -o -w all to warn all, -o to create the actual executable, and then omega.c as the source file name. So compile the program, everything compiles, and then I just run the program itself. In Linux, I have to do a // because without the // it doesn't know where omega is, because the current working directory is not on the path variable itself. So that's why it doesn't even look in the current working directory unless you tell it and say that, yep, it is in the current working directory. Now, for those of you who have Power accounts, you can do it on the Power server. Okay, every single step that I do here, you can just replicate on the Power server. If you're not using the Power server, then you can also use code blocks, code : blocks. Then there will be a GUI type of thing, and if you know how to set it up on the command line, I would assume that you know how to set it up using code blocks. Except in code blocks, I'll show you where to set up the arguments to a program. Okay, there's a particular place you can set it up. All right, so I'm just going to run the program, and I'll say this is lame. Okay, press the enter key, and guess what? It tells me this comma is comma lame. How did it pick up this? It's argv1. How did it pick up is? argv2. And then lame is argv3. But those are not even numbers. You're correct. It only picked up those as strings. So that means once you have the strings, you have to convert the strings to the values. Okay? Those are going to be, you can assume those are base 10 numbers. Okay? So you don't have to deal with base conversion. Okay? All right. So what if I don't give it enough or too many parameters? Blah, 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 blah. It complains and says there's not exactly 3 arguments. What if I give it less than that much? Well, it tells me not exactly 3 arguments. So now the question is, yep.
Why is argv4 not 3?
It's argv 0, 1, 2, and 3. Those are the 4 arguments.
What is 0?
That's a good question. How do we find that out without changing the program? GDB. Okay, for those of you who have taken assembly with me a long time ago, you know that GDB is one of the best tools for debugging programs. All right, so we'll GDB omega, and when in GDB you can list a program, set up a breakpoint, and we'll set up the breakpoint on line 4, which is the first line of the entire program, and then we'll say run, and then use 3 words again. Okay, 1, 2, 3. Okay. Press the enter key. So now we are on line 4. So we can now print argc. It is in fact 4. But we also want to know what is argv0. And that turns out to be the path to the executable itself. Now this is not my standard. It is not even a Linux standard. It is a standard of all Unix/Linux based system. Okay, it's when you invoke or when you run a command line program, the path to the executable itself is always argument 0. Okay? Whatever you type after that will be argument 1, 2, 3, and so on. And it always count from 0, so that's why even though argv3 is the last argument, the count is 4, because we are starting from 0. Is that okay? So based on this, you kind of have to think about, okay, now I have access to the individual things, but how do I convert these things into numbers? Because they are strings at this point. Okay, there are many ways to do it. You can do your own parsing if you want to. I guarantee that when I test it, I will not test with error cases, so you don't have to check for errors. So you can do your own parsing if you feel like it, or if you do not feel like it, you can always use ATOI as a function. Okay, so if you're on a Linux system, you can always say man ATOI, which stands for the manual page. So ATOI, ATOL, ATOLL, okay, those are all conversion subroutines. You give it a string, it gives you the value of that string, assuming that string is a base 10 number. Is that okay? So you just pass argv1 to get the number of experiments. You pass argv2 to get the number of choices per trial, and then you give it argv3 to see whether it is with or without replacement. So are we good so far with this? Okay. So what if you don't use Linux, like 90+% of the population? You don't have the man page anymore. Okay, so what do? Google it. Very good. Okay, there you go. You know the name already, so you just Google ATOI. You can even Google for ATOI examples or ATOI tutorial. I think you just look at one line of code, you know what to do with it. Okay. All right. So now we know how to get to the arguments. We know how to convert a string into the value that it is representing. So here comes the next, which is the most difficult part. How do we get this done? Because now you can get to the number of trials per experiment. You can get to the number of choices for the first trial. You also know whether it is with or without replacement. So I would guess that you need a representation of a set of some kind. Okay, because the generator itself, in mathematical definition, does make use of the concept of a set. So how do you implement a set in C and C++? Yep. I think bit mapping is probably the easiest way to do it. Okay, so what is bit mapping? Bit mapping is mapping a bit of an integer to the presence or the absence of a particular element. Okay, so allow me to illustrate, and I'm going to use, I'm not sure whether the tablet is a better way to do it or whether I should use a spreadsheet to do it, because both can be used for that purpose, but I think free editing may be a little bit easier in this case. So I'm going to use my tablet for this. Has anyone heard of that term, bit mapping? Kind of. Okay, maybe not. Okay. Okay, so I have to start with this question. Does everybody know how a number is represented in binary? Okay, all right, so that's good. So because that's really important for this particular discussion. And I need to get to my lecture notes. And then start up the screen copy from here. Oh, I haven't connected the cable yet. I can see why people like wireless technology. This is 1189, 418. There we go. Okay. Try one more time. Okay. So bit mapping means, you look at each bit of an integer and you say that bit is representing the presence or the absence of a particular element. So we'll start with a very quick review of what a binary number is and how we use individual bits, zeros and ones, to represent values. So we look at, let's say 201, okay? So we look at this number and go like, this is in base 10, by the way. So we ask, how do we represent this as a base 2 number? Now the cool thing about base 2 number is it's either the presence or the absence of a power of 2. You never really have more than one of each power of 2, which makes it kind of cool and easy to do. So we have 128, and we definitely have a 64. So these two together is going to account for 192. So that leaves us with 9. Okay, 9 is pretty easy. It's 8 plus 1. Okay. So plus 8 plus 1. So we look at these four numbers. And these are all powers of 4. So now we have to figure out, okay, but which power of 4, excuse me, powers of 2, which power of 2 are we talking about? 128 is 2 to the power of 7. 64 is 2 to the power of 6. 8 is 2 to the power of 3. And 1 is 2 to the power of 0. Then we convert, right at this moment, we convert into base 2. Because 2 to the power of 7 is 1 followed by 7 zeros in base 2. 1, 2, 3, 4, 5, 6, 7 in base 2. 2 to the power of 6 is 1 followed by 6 zeros in base 2. 2 to the power of 3 is 1 followed by 3 zeros in base 2. And then 2 to the power of 0 is just 1 in base 2. You add up these numbers, you go like, but we haven't really talked about base 2 addition. Well, it has no carry. Okay, it's not possible for this addition to have carries. So even though you do not know how to add numbers in other bases, it's the same way that you do it in base 10. Okay. So we end up with a 1 as the least significant digit, followed by 2 zeros, and then another 1, another 2 zeros, and then a 1 and a 1. Okay? And this is all in base 2. Is that okay? So that is basically how a value, which is 201, is represented as a base 2 number, which is 11001001 in base 2. So are we okay so far with that concept? Okay? But I can, instead of looking at this as a number as 201, I can now look at this as, okay, A, B, C, D, E, and then G, H. This is one way to look at it. What? I don't get where this is coming from. Well, what if I look at it this way? Bit 0 is corresponding to A. If it's a 1, A is there. If it's a 0, A is not there. I look at bit 1, and that's corresponding to B, C, D, E, F, G, and H. So it's a way of looking at the individual bits. And we look at each bit to say that, oh, that is really just telling us the presence or the absence of a particular lowercase English letter in the alphabet. Is that okay? So let me just be absolutely clear about this point. So I'm going to use a different color so it's highlighted. So this is corresponding to A. If it's a 1, A is there. If it's a 0, A is not. This is corresponding to B, C, D, E, F, G, and H. So using this particular way of looking at the individual bits of an 8-bit number, I now have the ability to represent a set that can have up to 8 elements from A to H. Is that okay? Any questions about this particular way of representing a set? We are making it explicit. Each bit position is corresponding to a particular element. If it's a 1, the element is present. If it is a 0, the element is absent. Is that okay? Now, if you want to say, but I don't like that convention. I like to say, if it's a 0, the absent is present. If it's a 0, the element is present. Be my guest. That's fine. But this makes more sense to me. Okay. But the homework assignment specifically say A to Z, right? This is only taking care of 8. So what do? Use a longer integers, right? A longer integer. a regular integer in a 32-bit or 64-bit architecture is already at least 32-bit wide. So if you just say int, that's going to give you a 32-bit integer already. So that would be more than enough to deal with what we need to deal with in this program. Is that making any sense so far? Okay. But if you really want to make sure that whatever int you use has enough bits to represent from A to Z, this is what you can do. So let me just kind of go back to this program, which is called, what was it again? Omega. Okay. So I'll show you another trick. You can pound include stdint.h, standard integer.h. Now the cool thing about this is now you can define your own type. You can say type def uint32_t as a set. What does that mean? Okay, so type def, hopefully your C class got a chance to talk about type def. It really is just saying that the following type also has an alias of the third thing on that line. Okay, so type def in this case is saying uint32_t has an alias of set. Every time you say set, it really is saying uint32_t. So now the next question is, but what is uint32_t? I like your answer. You're already thinking about it, aren't you? Google. And I said at the beginning of the class that I could not read mind. Okay, so what is a uint_32 uint32_t? It really is just an alias to guarantee that your integer, the variable created by that name has exactly 32-bit wide. It has 32 bits. So there's a uint32_t, there's a uint64_t, which guarantees that that particular unsigned integer has 64-bit. There's also a uint16_t for 16-bit wide unsigned integers, and also uint8_t for 8-bit wide in unsigned integers. So the use of these particular names is really helpful because it guarantees cross-platform compatibility. Because if you don't use these names and you just say int, well, int is 32-bit on a 32-bit architecture, but as soon as your program is compiled on a smaller architecture, an int may be only 16-bit wide. If you go for a larger architecture, an int may be 64-bit wide. So now, what range of number you can actually contain in your variables depends on what architecture or what compiler you're using, which means a program may work if you're only compiling it for PC and the PC is a 64-bit architecture, but the moment you try to cross-compile that to an Arduino, it stops working because on an Arduino, int may be 16-bit wide. So your program doesn't work anymore because it has an implicit assumption that an int is at least 32-bit wide. So I strongly recommend using these particular names not only for this class, but for all of your programming classes where the range that can be represented in your variables is important. Now, if you're dealing with something that goes only from 1 to 60, okay, then it really doesn't matter. Okay, the smallest integer can handle that. But on the other hand, if the range of numbers that you need to represent is exceeding, let's say, 2 to the power 32, then you need to make sure that the integers are at least 64-bit wide. Then the use of these names can become really useful. Okay, so it's not only for this class, but for all of your classes, this can be helpful. Okay, so now we got the other problem taken care of. We know that we're going to use a bitmap approach. So if we are using a bitmap approach, then we kind of have to think about how do we do all the unions, how do we do all the intersections, how do we remove an element from a set, because if we have trials without replacement, once we have selected an element, we have to take it out of the set before we perform recursion. Remember that part? So we need to perform all of those operations. All right, so how are we going to do all that stuff? I can just use this thing here. Now remember, we are not doing object-oriented programming, so I'm not going to do operator overload and all that crazy stuff, okay? You can do all that in your other classes, just not here. Okay, so there are a few things we need to know, such as element of, okay? So we need to find out whether something is an element of a set. So the first thing is basically it's 0 to 25 to represent A to Z. So that can be just a very small integer. So you can say uint8 underscore t, which is representing the element. And then we have a set as the second argument. And the question now is, how do we know? How do we know element E, which is, when you print it out, is A to Z as a character. But internally, when it's stored, you can store it as 0 to 25. Does that make any sense? Because they correspond to bit position 0 all the way to bit position 25. So how do I know whether an element is in a particular set or not? And a set is bit mapped. We're using a 32-bit integer where each bit is representing whether an element is there or not. How do we do it? So I'm going to give you the solution, but then I will explain what it is, how it works. Okay. So 1 shifted E many times, and then do a bitwise AND with S. That's all we need to do. Okay, so now we have to explain these operators if they are new to you. So are they new to you, or are they kind of like, yeah, we know how to do that? Because they are actually operators in C and C++. So it all depends on whether in CISP 360, whether your professor introduced these what we call bitwise operators or not. They did not. Yes, okay. So I see some nodding and some turning, which is kind of what I expected, because these are kind of, most people do not find them useful, but they're actually extremely useful at the lower level, okay? So it really does not hurt to understand these operators because they are actually really useful. So let's explain these operators first. And the best way to explain these operators, okay, is GDB. I'm not kidding. So we go to GDB without even running a program. So we say, give me 1. That's 1, cool. Give me 1 shifted 1 times. That's 2. 4. What do you think then is the next one? 8, 16, and so on. So what is going on? Well, the other thing that's really neat about GDB is you can print a number in binary. You cannot do that in C. C does not have the built-in ability to format a number in base 2. But GDB does. Okay? So let's try to do this in GDB and see what we're going to get. If I remember correctly, it's /t, but I could be wrong here. So, yep, it is /t. Are you surprised that 1 is 1? 1 in base 10 is 1 in base 2. Is that surprising? No? Okay. I was hoping not. Okay. What about this? What do you think it's going to look like? Where /t means in binary, and then we already know 1 shifted left by 1 is 2. You're close, but 1 too many, 0. It's just 1, 0. Okay. 2, 3, 4, and so on. In other words, this is the left shift operator is saying, give me something to shift, okay? And I'm going to shift it the number of times that you specify as the right operand. Is that okay? What do you mean by shifting? Left, yeah, go ahead. Okay, so left shifting means we are padding zeros to the right-hand side and then moving everything to the left-hand side. That's why it's called a left shift operator. Is that okay? Cool? All right. All right, so we understand one of the operators. The other operator is an ampersand. but it was not a typo. I know you guys know, but aren't we supposed to use double ampersand? Well, double ampersand is called a logical AND operator, which is the proper one to use when you have Boolean expressions on both sides. A single ampersand is called the bitwise AND operator. The bitwise AND operator is a little funky because what it does is it performs an AND operation for each bit position. What do you mean by for each bit position, right? So the first thing we do is to give you, I'll give you an example, okay? So I will do this. I have to pick a number where it makes a difference. So, okay. What do you think this is going to come out as? 13 without 0x in front or anything funny is just a base 10 number. So 13 as a quantity printed as a base 2 number, what is it going to look like? You just have to think about a summation of powers of 2. 13 is 8 plus 4 plus 1. So it's going to look like 1, 1, 0, 1. It doesn't have a 2, that's why we have a 0. Okay, so we'll print this out and go like, okay, it is 1101. And the next number I need, I'm just going through my mind because I got a number picked out already, is 1010, which is 10. Okay, there we go. Okay, 1010 is 10 because it has a 2 and an 8. Okay? So now the question is, what is the AND of these two? So if I use print in binary, okay, 13 and 10, what do you think that's going to be according to the C standard? What can this guarantee, and what are the possibilities? Yep. It is exactly, okay, I like that answer. It is simply true. But C has no concept of a Boolean. So anything that is non-zero is considered true, which means this operator, AND, which is a logical AND operator, the result of this is really just true and true, which is true. So it can choose any one out of 4 billion non-zero values of a 32-bit number. And they're all considered correct because all of those are non-zeros and they're all considered true. Okay? So when I press the enter key, I just have to say, is it non-zero? Yep, that's non-zero to me. What about a bitwise AND? In other words, instead of performing a double ampersand, I only perform a single ampersand. What do you think that's going to do? Well, it's called bitwise AND, which if you kind of try to understand the words of that particular operator, it's performing an AND operation on a bit-by-bit basis. It's taking bit 0 of the two operands. So it's taking bit 0 of 13, which is a 1, taking bit 0 of 10, which is a 0, perform an AND. That becomes the result. It becomes bit 0 of the result, which is going to be a 0. Okay? And then it's going to take bit 1 of 13, which is a 0, bit 1 of 10, which is a 1, perform an AND operation. 0 and 1 is also a 0. So that gives me 2 zeros as the 2 least significant digits. Then we'll take the bit 2, which is a 1, with 13 and a 0 for 10. So that's going to be another 0. But the most significant bit that we have shown here, which is a 1 for 13, it is also a 1 with 10. That would be 1 and 1, which is a 1. But that's going to be bit 3 of the result. So that means the result is going to have bit 3 being a 1, and then bit 2, bit 1, and bit 0 all being zeros. So that will give you 1, 0, 0, 0 in base 2, otherwise known as 8, because it is 2 to the power of 3. Is that okay? So let's double check. Okay. There we go. It is 1 0 0 0, but it's printed in binary. So let's print it not in binary, but in base 10. And not surprisingly, it is just 8. So is that okay? Does everybody understand what is a bitwise AND operator? It performs an AND operation for each bit position. And then the result of that AND operation is also going to the corresponding bit position of the result. Is that okay? All right. So, if that is the case, what do you think? Okay, let's go back to the source code first. So I'm going to go back to the source code. So can everybody see how element of is going to work in this case? Because E is a number from 0 to 25, because we can only have up to 26 elements, and since we count from 0, so that means E can only go from 0 to 25. So one left shifted E many times is what we call a bit mask, because that number has one and only one position of the bits being a 1. Everything else is guaranteed a 0. Okay, so we call that a bit mask. So the bit mask is then bitwise ANDed with the set itself. The set can have a whole bunch of zeros and ones, okay? But we're only interested in one position. And that is focusing on just one single position and go like, well, is the bit corresponding to the element I'm interested in, is that a 1 or is that a 0? This expression will return a 0 if it is a 0, but it will return a non-zero value if it is not 0. Are we doing okay so far with this? Yep. No, E is really just an integer. E is an integer from 0 to 25. Yeah, so until we're printing, we're only dealing with numbers like 0 to 25. But when we print, instead of printing 0 to 25 as numbers, it is just easier to read as characters, as letters. Okay. Okay, so the next thing we need to do is to create a set that is a singleton set, which means it has one and only one element. Okay, so we have a singleton set, and the element that we want to be in the set is union8_te. So now the question is, how do I create a set where it has one and only one element, and that element is specified as my parameter? Yep. 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 Exactly. That's all we need to do. So we just say return 1 shifted E many times. That's it. Okay, so let's think about this. So let's say I want to create a set where E is the only, well, I shouldn't say E. Let's pick another one. Let's pick G, okay? So let's say we want to create a set where G is the only element in the set. Is that okay? So you count A, B, okay, A is 0, B, C, D, E, F, G. G is corresponding to the number of 6. So E should be a 6. So this becomes 1 shifted 6 times to the left. So we're ending up with a binary bit pattern where all the bit positions are zeros. In other words, all the elements are missing except for 6. And 6 is representing G in this case. So it becomes a set with only G in it. And that's why it's called a singleton set, because it only has one single element. Is that okay or not? Are you guys understanding what a singleton set means? It's a set with only one element, and the element that I want in it is specified by E. Is that okay? All right. So now we can start to ask more interesting questions. Okay. I'm not sure whether this is neat or not, but we'll set union. So we have set A, and then we have set B. So what do you think is the union between two sets, and each set is represented as a bitmap? A bitwise OR, very good. Okay, so I like that extrapolation because I haven't really talked about the bitwise OR. I just talked about bitwise AND. But the bitwise OR operates exactly the same way. So you take one bit position of the left operand, you take the same bit position of the right operand, perform a OR, okay? Whatever the result of that is, which is going to be a 0 or 1, becomes the value of the corresponding bit position of the result. Okay, so yep, so that's just A, return A, bitwise OR B. Logical OR is bar bar, so bitwise OR is just a single bar. Okay. Well, let me try this one. What about intersection? How do I find the intersection of two sets, both represented as bitmaps? Bitwise AND, very good. So we just return A and B. Oh, okay. Doesn't look too hard. Okay. Is there a way for me to test whether a set is empty or not? Okay, so let me give you the prototype and you guys tell me how we do it. So it's going to be an int because we just need to know 0 versus non-zero. So we'll say is empty set. We'll give it a set A. And I just need to know whether it's empty or not. How do I know that? What does an empty set look like? Well, no, we have to return the opposite because the naming of the subroutine means if it's empty, we want to return a non-zero. If it is non-empty, then we want to return a 0. Okay, so we need to negate it. So technically speaking, this will do. Is that okay? Now, if this is not looking very nice, you can always say A equals to empty set. And then we define what an empty set is. Okay, set empty set. Does that work? Is everybody buying this? An empty set is just 0. Okay, because we want something to represent the absence of A all the way to Z. So that means all the bits corresponding to A to Z, they all have to be zeros. Okay, assuming the 6 bits that are left behind are by default all zeros. So that means an empty set is really just the number 0 itself. But if you want to convince yourself that but this is actually a set of no elements, you can imagine in your mind, instead of saying it is a 0, it is 0 0 0 0 0 0 0 0. Repeat that 32 times. Then you will see that okay, so the position corresponding to A is a 0, meaning A is absent. The position corresponding to B is a 0, meaning B is absent, and so on. So that will help you kind of visualize and go like, okay, I see how 0 is actually representing the empty set. So we can just compare a set with the empty set and say, if it matches the empty set, it is empty. Otherwise, it is not empty. Is that okay? All right. What about subtraction? That's a little interesting one. Okay, so we have a difference. Set A, set B. So this one is a little bit more awkward, right? I mean, we are trying to calculate what is A minus B, but these are sets, okay? And the normal subtraction is not going to work. So how are we going to do this? Now, let's review what is subtraction for set operations. A minus B means it is a set that has all the elements in A that are not in B. Okay? So we're looking for everything in A that are not in B. Okay. So we'll start with the 2 ingredients, and then we'll find out how to do it. So we'll start with A and B. We know for sure that those are needed for whatever operation we need here. I think A is fine by itself, okay, because A is everything that is in A already, okay, that's cool. But we also want to clear the bits corresponding to things that are in B. So now we need to think of a way to clear a bit. If it is a 1, I want it to become a 0. If it's already a 0 to begin with, we can just leave it alone, okay? So what can accomplish that purpose? A bitwise AND can do that, okay? So a bitwise AND operation can clear a bit. Okay, so we'll throw that ingredient in here and say that, okay, we need a bitwise AND. But we don't want a bitwise AND with B, because otherwise we're just looking at the intersection between the two sets. Okay, so we want to look for everything that is in A but not in B. We need to negate it. Okay, so bit positions corresponding to things that are in B, we need to turn those ones into zeros. Is that okay? So it's a bitwise NOT operation. Bitwise NOT is the tilde symbol. So the tilde symbol means bitwise NOT, and I can never really remember the operator priority, so I always just use extra parentheses to make sure that we don't have any confusion. In this case, I don't think we should have any confusion because it's a unary operator. Okay, so tilde B is a bitwise NOT operation. How does it work? Every 0 becomes a 1, every 1 becomes a 0. That's all it does. Is that okay? And I think this is all we really need. These are all the basic operations, all the basic set operations that you will need in the program. Oh, you might need one more, which is finding the next available element in a set. You might need that too. But you can just scan a set too. You can just use a for loop and just scan the whole thing and see when you find something that is in it. So are we good so far? Okay, so this is one set of tools that you will need. And let me just compile the program first, just to make sure that it does compile. Okay, so we'll do a GC. There you go. Yep, that's compile, and I think they're semantically correct. Are we good so far? So the next idea is the concept of a recursion. Okay, so let's go back to the notes first, because all of those, the algorithm itself is going to be based on the mathematical recursive definition of the outcomes. So for that, we have to go back to one of the earlier modules that we have seen. I think it is just counting. So if you go back to counting and you go to permutation outcome set of experiments without replacement, and we go straight to the recursive definition, which is down here. So this is the recursive definition of generating the permutations. Okay. So when you look at this, you go like, wow, it looks like it's a lot of work. Okay, because and we are talking about tuples too. We are talking about Cartesian products, and the method that I just talked about doesn't really work well with Cartesian products. So how do we deal with something like this? So what you need to remember is the so-called Cartesian product is not necessary when you're implementing the program. You can use an array to help you keep track of what did I choose for the first trial, what did I choose for the second trial, what did I choose for the third trial, and so on. So you can use an array to keep track of what you have chosen for earlier trials, so that when you are ready to print the entire permutation, you can go back in time and track down what you have chosen earlier. Okay? So the Cartesian product is really not needed in terms of the implementation of this program when we just need to print out all the permutations. We do not actually need to represent each permutation exactly as a permutation. Okay? All right. So, but we still need some kind of recursion, recursive scheme, because we also need a mechanism to go back in time and find out. But what did I choose for the first element, for the first outcome of the first experiment? What is the outcome of the second trial, third trial, and so on? So, any ideas? Any ideas of how in a recursive algorithm you can go back in time and ask an early invocation and say, tell me what you have chosen for the first trial, in the second trial, and so on. There are many ways to do it. You can maintain your external quote-unquote stack. Okay, that's one way to do it. This is also why cisp440 is actually useful, because in that class, I hope they talk about the concept of a stack, which is also called a last in, first out. So that concept is really helpful, because what you're really doing is using a stack. Because what you're doing is you're saying, what did I choose as for the first trial, for the second trial, for the third trial? What do I have left at this point? Well, A, B, C are gone, and that we use a set representation, but we can use D, E, F, G, and so on for the next level. Okay, so that's why the concept of a stack can be useful in this case. But a stack is also implicit in a program. All right, so let's go back to here, and then revisit. I'm going to use another program for this, so I'll call this recursive.c, and then we'll do a recursive subroutine, and we'll make it pretty much as simple as possible. That would be very simple, but then it's not going to stop with it. So we probably want it to stop at some point. Okay, fine. We'll make it stop, and we'll say if I, then we do a recursion with I minus 1. Otherwise, we stop. Okay. Well, that should do it. And then this time, main doesn't really do much, so I don't have any arguments being passed here. You know what? I'm going to show you guys how to do the conversion thing. So I'm going to show you how to do it. Const char star star argv. So this one, it's going to have some of the elements that you need, but not all. So if argc is 2, we can do the following. And I cannot remember how to use atoi. I don't remember which pound include you need with atoi. So what do? Google is 1. But since I'm in Linux, I can use man. Okay, so I can say man atoi. And so it shows me what header file I need to pound include is stdlib.h, standard library.h. So I need to pound include that file. Then I can use atoi. Okay, so just take a note of that. And then we say pound include stdlib.h, standard library.h. And then here, let's say we don't have to do error checking, so we are guaranteed that it is actually a number. Then we can go ahead and say, what do I need to do here? Oh, right, integer number of levels is going to be atoi, and this time it's argv bracket 1, not bracket 2, because we come from 0. And then we pass that to function f, number of level. And that's my entire program. Okay. Is that okay so far? This program, this recursive subroutine f, is going to stop at some point, okay? Because when I pass a number to it, it will say if it's non-zero, then we'll decrement it by 1, do the recursion. So eventually, okay, it's going to be 0. When it is 0, it stops the recursion, and then we'll go backtrack and unroll the stack like that. Okay. All right. So once again, I'm still recording. So you don't need to frantically write down everything. But if you have, like a really good understanding of the material, and you want to write down in your own words of your understanding of the material, that you want to write down. Okay. But if something from the screen, there's really no need to copy everything verbatim onto your own notes. Okay. So this is the program we'll give it a try, called Recursive. GCC-G- warn all -o recursive recursive.c. There we go. GDB recursive. And then we'll put a breakpoint somewhere. I'm going to put a breakpoint on line 4. In other words, every single time at the entry point of f, I'm going to stop, okay? Because I want to show you how to look at a recursive subroutine from a debugger, okay? Because that's going to be useful. Because at some point, you might end up with an endless recursion, and you want to know what happened to my parameters, okay? Did I pass something unreasonable to the next invocation? So you will need to kind of backtrack and find out how you get to a certain point. All right, so we'll run the program. And remember, because we are interpreting the number of arguments, and we want to have exactly 2, so I need to give it a number. Let's say we want 5 times of recursion. So we'll say run 5, okay? So at this point, we're on line 4 right now, and it does tell you, okay, if you look at GDB, it tells you that we are in function f. Not only that, but parameter I is 5 at this point. Is that surprising you? No, the program does that, right? Whatever you pass on the command line becomes the first argument on the first invocation of f. Okay, no surprises here. So now we continue, okay? This is the second invocation, f of 4. Is that okay? It's recursive, but when we perform the recursion, we're only passing I minus 1 to the next invocation, so the 5 becomes a 4, okay? The 4 becomes a 3, the 3 becomes a 1, the 3 becomes a 2, the 2 becomes a 1, and then the 1 becomes a 0. Okay, so right now, the question is, then what happened to all the previous invocations? Okay, without the debugger, it is very difficult to visualize what is happening. Okay, because you can kind of have an idea that there are multiple levels of the invocation of f, but where are they? Okay, are they on top of each other? Are they overlapping each other? Are they overwriting each other? What is going on here? In a debugger, the best thing you can do is what we call BT, or backtrack. Okay, so when you type BT, it shows you something like this. What is it telling you? It's telling you that we are currently in f with an argument of I equals to 0. I is the name of the parameter. Okay, not surprising because this is where we stopped. But how did we get here? We got called from f. But the caller, even though it is f, it has an argument of 1. How did that one got called? It got called from f when I is 2. How did that one get called? It got called from f when I is 3, and so on. So it gives you the entire history of how we got to where we are at this point. And that is really helpful. Okay? So you might have some local variable in f, and you go like, well, but at this point, I can only, when I print I, okay, so if I print I, what do you think is going to be the result of that? Which I do you think is going to pick up? The most recent one, which is the value of 0, okay? Okay, not very surprising, right? Okay. If I have any local variables in f, it will only pick up the local variables of the last invocation, the current invocation, which is helpful. But what if I am debugging my program and I say, well, maybe I messed up something earlier in the previous invocation, and I want to print the local variable of an active invocation, but it's somewhere in the history here. What do I do? Well, backtrack works well with another command called frame. Frame, frame. So frame allows you to change your quote-unquote cursor, okay, frame refers to these numbers. So we are by default at frame 0, which is the current frame. So if you say frame 1, it means the frame previous to the current one. Frame 2 means 2 frames before, 3 means 3 frames before, and so on. So if I say frame 4, okay, and, well, it shows the answer already. It basically says, oh, frame 4 is the one where the parameter I is 4. Okay, so if I say print I, obviously it's going to print 4. But if I had any local variables, I would be able to print the value of a local variable of a previous frame, even though the execution point is not there anymore. Is that okay? Now this is really, really useful because as a local variable inside each frame, you can have its own set. So each frame, each invocation has a local variable that is a set, so that that set can keep track of the alternatives that you can choose from for its own choice, for the outcome of that particular trial. Okay, so let me say that one time, okay? Each frame in recursion corresponds to one trial, okay? So you basically, the number of recursions, the number of levels, the number of frames should correspond to the number of trials. When you're at the very last one, you would realize that you're at the last one. And then when you're at the last one, then you have several options to find out what the entire outcome is. You can either maintain a global variable or something else to keep track of the choices that have been made prior to you, or you can inquire and track back in time and say, hey, previous frame, what did you choose as the outcome of your trial? And then from that point and go back one more level and ask the one before, and then the one before, and then the one before. Then you can come up with a quote-unquote linked list of the entire thing. So that brings me to another question. Have they started to talk about linked list in 430? Finally. Whew. Okay, good. We got 10 more minutes. Okay, so now I can talk about a technique that combines recursion with linked lists. Yes?
When is all of this due?
Next week.
Oh, okay.
Is that, I think, given all of these pieces, you probably have enough time. But I'm going to take roll first because I keep forgetting to do it almost for the entire semester, right?
The first time.
Yeah, well, not the first time, but one of the very few times. All right, so I'm going to let you guys pass it along. Okay, so we're going to talk about a linked list. And we'll combine a linked list with recursion. Okay, how do we combine those things? So obviously we're going to use a struct. A struct is the same thing as a class where every member is public. Okay, so it's really a very crude concept compared to a class. So struct, we'll call that, I don't want to use frame because otherwise it confuses with the frame in GDB. So we'll say level, okay? So this is a level, okay? And in a particular level, in this case, we'll keep track of several things. We'll say what is the number of that level. And then we'll also do something like this. Struct level previous. Okay, where do I find the previous level? Is that okay? All right. And I'm going to change the parameter here to a pointer to a level. So struct level pointer to a level. There we go. So I don't have an I anymore. And then each invocation has its own level. So struct level L. And then we'll say L. Let's see, what is the best way to do this? When I do this exercise, I'll change it every single time a little bit. So I'm going to say if p level num, then we continue to do the recursion. Then we say L dot num is p level num minus 1, and then L dot previous is p level, like so, and then we pass the address of my own struct level down until we get to the last one. And then the main is going to change a little bit as well, because the main has to also have a struct level L. L dot num is num of level. And we don't have any previous at this point, so what do you think previous is going to be? Null. And what is the other name of null, which is a lot easier to type, is 0. Yep. And then we pass address of L along. Okay. So the program still does pretty much what it was doing before, except at the very last level, it has the ability to go through a linked list to find out the number of each level prior to it. Okay. So let's check out how this works. Okay. Well, first of all, does it compile? Because I'm notorious of forgetting details like that. Okay, not compile. Fine. So we'll fix it. Line 25 expected equal. Okay. Right. Okay. Try again. Does compile. Okay. So we say GDB recursive. Once again, we put a breakpoint on in the entry point of F. Now, if you're in GDB, one way to do it is to say break at F. Okay. So if you do a BF or break F, it automatically puts a breakpoint at the beginning of the named function, which is kind of handy. And then we can say R. Okay, let's do 3 this time. Okay, because otherwise it's just a little bit too many levels. Okay. So this is the first level. We continue execution. Second one. And this is going to be the third one. I think we have one more level, but I'll just double check. So we say, what is P level pointing to? So P level is pointing to a structure where num is 1. So we have one more level to go. So we say C continue. This is the last one. So when we print what P level is pointing to, it is pointing to a structure where num is 0. But it has a previous pointer. So if a structure has a previous pointer, what are you itching to do? Find out what it is, right? Okay. So now we say, oh, okay. So tell me what is the previous of the current level. Give me that structure. Okay. And it goes like, well, it's level 1, and it has its own previous. What are you going to do next? Track that down. It's level 2, but it has its own previous. If previous gets to 0 or null, then we know, okay, we're at a dead end. Okay, we can't go any further. And what do you think this is going to do? It's level 3, right? But level 3 also has a previous of null, because that's the ground state. This is what main has. So we have backtracked our entire way from the last invocation to the first invocation. So what can be useful about this approach? You can find out what remember what I said earlier? Each frame or each recursive layer is one trial, right? So you have one trial at the beginning, another trial as your second trial, third trial, and so on. When you get to the very last trial, what do? You need to find out what is the permutation at that point. How do you find out what is the permutation? How do you find out what trial 1 has chosen as its outcome? What trial 2 has chosen as its outcome? Backtrack. The previous pointer can be used like that. Then you just have to retrieve all of those things, print it out, you're done. As your last level. You backtrack to the previous one and say, well, okay, we have used this one. Do we have any more available choices? If it has more choices, change the outcome of that particular trial to the new choice. And then do the recursion again and go like, okay, you go and do it again. Is that making any sense? We are almost running out of time. We got 2 minutes left. But this is a very important thing to point out, is what else can we put in here? You can put a set in it, right? You set my choices, right? My available choices, I should say. Available choices. Okay. What else? Huh? Whatever is left. When you set up for the next invocation, that invocation is responsible to set it up for itself. But there's one thing that you have to track as well, is what is your current outcome. Okay? So, it's not going to compile because I'm combining the two programs into one, but you can basically say, my current outcome, which is important because that is basically what you would use to combine to become the outcome of the entire experiment. Okay? And anything that you feel that you need to keep track of. So instead of having individual local variables per level, you just have one single structure as your local variable. And that one single structure contains everything that each invocation needs in order to do its operation. Then the very last invocation now has access to every variable, every property that has been used in previous invocations, which include the outcomes of each trial, which is what you need to print. So this is one of many ways to do it, not necessarily the easiest way, but in terms of data structure, it does make use of a linked list in a very weird way. But it's still a linked list. Now, just a big, huge reminder, do not new, do not delete. There's nothing to new here. There's nothing to delete. Why not? How do I create these structures? It is a local variable. Okay, so it's on the stack. When you return from the subroutine, it's automatically cleaned up. There's no need to delete. When you call a subroutine, it's automatically created. There's no need to new. Okay, so do not new nor delete because these are all on the stack itself already. Is that okay? As I said, this is one of many ways to do it. Okay, but I like to point this out because this gives you the option of you can do a lot of stuff using this particular method. All right. All right, it's 5:20. I'm going to let you guys go because I have a dinner to finish and 40 minutes before my next class, 6 to 8 o'clock.
So yeah, you're just giving us a toolbox so we can kind of just do what we want.
Yes. And you can ignore the entire toolbox too.
Yeah.